Well, I'm the next speaker, and with the aid of Pedro, we are going to show you the VLAB cyber infrastructure. This project actually was funded by a program of NSF program called Cyber Discovery and Innovation. The program was discontinued for a while, but exists again. It's available again. So this was essentially our solution for the problem of, okay, let me, this is a type of solution we envisioned to the problem of doing, computing high pressure, high temperature elastic constants of materials that results in a very, very large number of jobs. And actually, this type of solution is usually used for parameter sampling calculations when you have a very large number of calculations to perform. In our case, parameters are volume or pressure. Temperature we use the quasi-harmonic approximation, but the parameter is the Q, number of Q wave vectors for phonons to be sampled, strains. So it was developed to facilitate the execution of complex workflows and multi-parameter sampling calculations. And elasticity, high pressures and temperatures is the typical type of calculation that I'm referring to. So I'm going to tell you a little bit about the features, the performance of the system, and the overall requirements, and how it supports workflow, and why is it called a service-oriented architecture. So I think this is the quasi-harmonic approximation that I have been referring to. And just to calculate a thermal equation of state, we needed to optimize structures to, each one of the optimizations are self-consistent. It's a calculation. It's a high-performance parallel calculation using 10 or even 100 of cores. So 10 pressures, and at each of these pressures, 10 Q vectors. So here we have 100 executions, 100 tasks already to execute. And for elasticity, we have 10 times more if we apply strains, 10 strains per volume. So 1,000 tasks to monitor, to prepare inputs for, to submit, to monitor, to gather results from, to prepare inputs for the next stage. It's really an overwhelming task for one researcher. Usually teams of researchers do this type of calculation. So the VLab provides a consolidated interface, a web portal, actually, that provides access to a set of tools. And the tools today are, for example, the Quantum Espresso, but it could be another software. You prepare inputs for all these programs within the Quantum Espresso through the portal. You can analyze results through the portal. There are several analysis tools and visualization tools. This system provides a workflow management, and you'll see what that means. Task distribution and task recollection is part of this management, but monitoring is part of this management as well. And I will show you that. Collaboration through shared access to resources is also possible, and results. For example, if you have a team of collaborators working on one project, the participants can view the project running at the same time. And that is just the level of priority that you give to your project, who you want to allow to see the results that are being produced. In VLab today, we are gathering results of successful projects and collecting on a database. Also, if we have 1,000 tasks to run, we want to leverage the capabilities of distributed resources. We want to harness the computational power of as many computers or we want. They may be in a grid, like a teragrid, or they may be scattered resources or other forms of grids. This system is based on web services, so we don't have necessarily to use a grid system. And also, VLab was built to be easy to implement new tools and easy to use. So the workflow, typical workflows, they are like this. You prepare input in the portal, and then, for example, if you want to calculate 10 pressures, 10 execution packages are prepared and dispatched to the compute nodes that you select. They may be one or they might be several. And the execution packages, they contain all the files you need to run. The input, pseudo-potentials, temporary self-consistent potentials that you generate but you wanted to improve, intermediate potentials, self-consistent potentials. In a cloud system, we also think that we would dispatch the web services to the nodes as well as the executables, but that's not being done today. But in principle, that could be done as well. So then there is the next step is the data recollection. You gather the outputs, select information from the outputs, and the information is satisfactory. You can go to the next step, visualize your results, or even intermediate steps, not successful, you can analyze your results. Or you can iterate. For example, you don't think the convergence is not satisfactory. You go back to the input, to the portal, and launch a second stage of optimization of your structures. So this iteration is possible. Or if you don't want to iterate, you are satisfied with the results of that stage, you can prepare inputs for the next phase and start the process again. This is what I call workflow management. The system manages the tasks that need to be executed. So the results always return to the source, the user, and the system has a tree-like service architecture. And this architecture has 4 stages. In the first 4 levels, in the first level, you have the portal that provides the interface with the user. The rest is essentially transparent to the user. In the second stage, you have a web service. It's a service-oriented architecture. In other words, it's a collection of web services that are distributed. In the second level, you have the heart of the VLab system, which is the project executor web service. This web service prepares the inputs and all the execution packages and send to another web service that's called the web dispatcher, the task dispatcher. The project executor also interacts with, collects data, interacts with the other web services, monitors the tasks that are being running, and collects outputs. Everything's done by the project executor and interaction with other web services. In the third level, you have the task dispatcher. This is the web service that sends the execution packages to the compute nodes. And in the lowest level, you have the compute nodes, and the web service running there are the task executors. So it's the crosstalk about crosstalk between these web services that gives the flexibility and the functionality of the VLab system. The task executor has access to programs and scripts that can be used to analyze results, like Fortran programs, such as to calculate thermodynamics properties or fit equations of state. And all results, all data and metadata that is generated during the execution of a project, they are all stored in databases, metadata databases, or pseudopotentials databases that are used, that are invoked to build to include in the execution packages and summary of calculations and results from calculations and so on. So I'm going to show an example of this. There is another feature that was built recently, which is bag of tasks. Bag of tasks. For example, thermoelastic properties is a petascale problem. You have 1,000 of tasks typically, and each task may use 100 cores. In itself is a high performance computing problem. So also the new resources that are coming online, they have a scheduling policy that gives preference to very large jobs or tasks that use a very large number of cores, 10 to the 3, 10 to the 4. But PWSCF, Phonon, the codes, the Fortran codes we use, they don't scale that well to these numbers of cores. I mean, they scale well to perhaps 10 to the second, 10 to the third, 10 to the fourth most number of cores. If we send individual tasks to these high performance systems, they are going to wait in the queue for a very long time. So what we do is collect a certain number of tasks within one bag, the bots, and dispatch these bots to different nodes or to one node. It doesn't matter. As a single task. So the scheduler in these resources will see the bag as one task. So it's one way to fool the system to get higher priority in these higher performance resources that are coming online. And this is the example that I'm going to show today does exactly that. So if you have M processes, M tasks, each one using N cores, K cores, the number of cores that you're going to need is M times N. This is a bag. This is an example of a bag. We call it a super task. The example that I'm going to show is you were going to see today. This result is not published and is not going to be available online in the near future. But you can go online today and see exactly what I'm going to show. This is the calculation of static elastic constant in Maudsley, right? We have approximately we have 8 volumes, but then we have 9 strains per volume. We have a total of 72 tasks in the last stage. But we have an extra stage here as the first stage, which is an approximate equation of state that speeds up the calculation very much. So, so this is the number of tasks that is submitted in each stage, and they are all collected in a single bag right now. And only one bag is dispatched to Itasca, our main computational resource here at the MSI. Each task in the first stage takes 2.5 minutes, 7 minutes in the second stage, and 1.5 minutes in the third stage. So in the bags, all the tasks in a bag run simultaneously in parallel. So if you had to run this whole workflow sequentially, it could last 3 hours and a half, not take into account the queuing time of each one of these tasks. And the number of cores that are necessary in the last task, and that's what it's important, is 3,204 cores. If we have access to 3,204 cores, the whole stage will execute in 1.5 minutes. So, so this is what I want to show, how it looks like. This is the interface. This is the portal that a user of VLab logs in, and we use Maribel's username. Oops. Do I know her, Pedro? Am I using her password? I don't know if I. Okay, so this is Maribel, and she's going to use her, these are her portlets. So these are projects